Okay. Hi guys. We're gonna do exam three review part one today. And I'm gonna start you off with notes because for this exam, all of these reactions are like the named reactions. They all look very similar, so it's hard to compare or like know what the difference between each one of them is. So I'm gonna give you notes on them so that you can compare, and that really helped me when I was taking my exam. So I would think it would help you. So then fast forward through these like or press like speed times whatever so that you can go through these fast. Let me give you the notes. Okay, so for your aldol reaction, right in purple. Yeah. Two molecules like okay of an aldehyde or a ketone reacts to form beta hydroxy carbonyl. Okay. And then loses H2O to form alpha beta saturated. Saturated. Okay. So it helps like I'm not gonna give you the mechanisms since running through notes, reactions, mechanisms, and synthesis would be like a little too long of a video. So then as I go through each one of them, like aldol, I'm gonna give you a reaction and I'm gonna show you the product and some tricks to like give you the product so that when you're doing the test you can find it fast. But it helps to look at the mechanisms while I'm doing this, so you should definitely do that. So I'm not gonna go too much in depth. So I'm gonna give you a random aldehyde, basic aldehyde, and a basic ketone. And so my product for this is going to be hydrogen, oxygen, double bonded. Boom. That'll be my product. And so it looks confusing, but there's like several tricks to like figure out the product really quick. So for all of your because these chapters are all enolate formations and everything. So you have to think about the alpha carbon because that's what we're doing when we're talking about enolates. We're deprotonating the alpha carbon in order to make an enolate. So we put a random thing. Okay, to make an enolate. So let me show you the resonance structure. Deprotonating alpha carbon, and notice how my nucleophile here is a carbon. So there's several products for these, but the one that I chose to make an enolate right here. And so yeah. So on that enolate, I'm just going to let me see. Cut this oxygen off and attach it to my alpha carbon. So this is my alpha carbon right here. And I'm attaching this carbon right here, this carbon right here, to all of this. To all of this. Right? So then you could have also had another product. You could have acted like your alpha carbon was going to be right here. So then alpha carbon right here. And instead you could have attached your aldehyde. So here's what I did. I kept my alpha carbon and I cut my oxygen off of my other compound and I just put this together over here. That's my product right here. And again, I'm going to go through several of these synthesis because I think it'll help. But these notes are already something like carried me. So, okay. So then for Clayson, two molecules of an ester react with each other to form a beta keto ester. Two molecules of an ester react with Okay. So two molecules of an ester react with each other to make a beta keto ester. Okay. So then, let me see. Hold on. Okay. Two molecules of an ester react with each other to form a beta keto ester. So I'm going to give you two random esters. I already have one written down. And I'm going to give you the exact same ester. Make a beta keto ester. Okay. So then here, beta keto ester is so like, okay, so let's say I'm looking at this part right here. This is my keto part. At the beta position, this is the alpha, this is the beta. At the beta position, I have a beta keto ester. So that's how I would explain that. Okay, but whatever. Two molecules of an ester react with each other to form a beta keto ester, and that's what your product will be. And all that I did here was I kept one of them the same. So this one the same. I just kept it the same. It looks like, oh, forgot that. It looks like this right here, right? So it has a total of 1, 2, 3 carbons, 1, 2, 3 carbons. Okay, so here again, we're talking about enolate, so we're deprotonating the alpha carbon. The alpha carbon on this one is going to be this hydrogen, right? The alpha hydrogen on this one is going to be this hydrogen right here. Okay. So then, let me erase everything. At this alpha carbon, I'm going to deprotonate the hydrogen, right? And so this hydrogen is going to come in and attack right here. And then we do our thing, right? So we know that the ETO is a good leaving group. So when we reform the carbonyl, this thing is going to leave. So then we're left with this whole group, which I just circled on this side, as well as this group right here, which is just this group right here. So then one of the esters is going to leave, but everything else stays the same. Remember, locate your alpha carbons because that's what we're dealing with. We're gonna move on to the next one. Again, I'm gonna go over some reactions of those. Charge my computer. For Deichmann, it's an intramolecular Claisen. So an ester reacts with an ester, basically. So I'm gonna put intramolecular Claisen. And again, look back at your Claisen and it says two molecules of an ester react with each other. So intramolecular means within one compound. So then in one compound, I'm gonna need two esters on there. And I'll show you again. So in one compound, it's going to react with each other. 1, 2, 3, 4, 5 ester. So here, I think it'll be cool if I drew it really bad, but it'll be cool if I just numbered this already. Notice how I have two ester groups on my compound, intramolecular Claisen. So again, we go to an alpha carbon, you can go to either one of them, but I'm going to start this one. And I'm going to start numbering because it's going to be important because you're cyclizing, you're making a cyclic molecule. So then it's important to count your groups. And you start with the alpha carbon. You can start at either one of them, but I'm starting with this one like arbitrarily. And so your alpha carbon is going to be your nucleophile, right? So once I deprotonate this, it becomes a nucleophile. Nucleophiles like to attack electrophiles, so the only electrophilic molecule I have here is at number 5. I also have it at the one that we didn't count, but it's not like this can attack this right here because we're already bonded to it. Like, we don't need to attack something that's right next to me. So then I'm going to attack something all the way over here. And so I counted 1 to 5. So what's going to happen is I'm going to make a ring that has 5 carbons on it. And then I'm going to number everything. So arbitrarily 1, 2, 3, 4, 5. Okay, at carbon 1, right here, I have an ester group. I have a whole ester group. And at carbon 5, notice how I'm attacking the electrophile, and then you break the double bond of oxygen, right? So we have a good leaving group on there. It's right, this right here. So we're gonna try to make that leave. So we're gonna reform the carbonyl and kick it off. So at that point, we're only gonna have a keto group. So then all I'm gonna do for my number 5 is add a carbonyl. That's all I'm gonna do, because I already kicked off the good leaving group. Okay. Yeah, that's the Deichmann. Let me change my color. I'll go back to for Michael. Michael I actually liked because this is like the cuprate reaction. So alpha beta unsaturated. And enolate form a 1,4 addition product. So then again, break it down. Alpha beta unsaturated, I'm gonna give you something random. Okay, so then this is my alpha group and this is my beta group, right? 1 carbon away from my carbonyl is my alpha group. So this is considered my alpha group as well. But in this compound, it's called an alpha beta unsaturated because in between alpha carbon and the beta carbon, I have a double bond. Code word for a double bond is unsaturated. So that's why this one is my alpha beta unsaturated compound. And then an enolate. So pretty much anything you can form an enolate with. So like an aldehyde or a ketone, something that you can deprotonate the alpha carbon with will be fine. So then I'm going to use just a ketone. Because again, I can deprotonate the alpha carbon right here and make an enolate. So both of these react to form a 1,4 addition product. Okay. Here, I told you already, I'm deprotonating the alpha carbon. And I'm going to... Actually, let me see. Yeah, I don't want to show you the mechanism because I personally don't remember it. And if I give you the wrong one, it'll throw you off. So then just know that we say 1,4 addition because we're counting the oxygen as 1. The carbonyl carbon is 2. The alpha carbon is 3. And then the beta carbon is 4. We're doing a 1,4 addition product. So at the 4th one, I'm going to add this whole group. That's all I'm doing. So then boom, boom, boom. Boom, boom. This is the new bond. And notice how I'm not adding any carbons. So then I'm going to count my carbons just to make sure. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I've added nothing new. It's just these 2 carbons together. And then the way that you find out this is the Michael reaction is you have an alpha beta unsaturated and you have anything that can form an enolate. So it's not too bad. Like the tricks are what make it a lot easier. And the tricks are easy to remember when you remember that all we're talking about here is the alpha carbon and the deprotonation of the alpha carbon. So then the Robinson annulation is the crazy one. So then let me choose my color. I'll choose orange. So Michael reaction, which is again your alpha beta unsaturated with your enolate, so all of that, with an aldol reaction. So notice how all these different names are just combining different reactions. So that's what like confuses me, but I don't know. Having these notes really helped me with that. So then I didn't give you a Robinson reaction for this one just because I think all that you're gonna need to know for that one is the mechanism. And I don't think they're gonna give you Robinson annulation for like a reactions page. So then yeah. But I'll show you what one will look like. So if I react these two, do I have my papers? Yeah. If I react these two, I'm going to get this right here. See how weird this one is. Yeah, the best thing to do for this one is just do the mechanism. I don't believe they're going to ask you any other question about this. So all it is, it's combining an intramolecular, it's Michael reaction with an intramolecular aldol reaction. Starting materials are alpha, beta unsaturated, and a carbonyl, anything that can form an enolate. And then you know how to form an enolate using any of the bases like LDA or the oxide, sodium oxide. And you should be good. Okay. There's a couple of more that I want to talk about, so I'm going to talk about it right here. Ignore this aldol condensation part. So I'm just gonna right there, just so I can make more space for myself. So malonic ester synthesis, you're gonna see something very similar, which is the acetoacetate one, acetoacetic synthesis. The only difference between those, because they're like kind of the exact same thing, the only difference between them is the starting materials. So for the starting materials in the malonic ester is literally malonate, so malonic ester. That's their starting material. And so what is this right here? Oh, I'm sorry. It's called diethyl malonate, which looks like this right here. So that's one thing you can have down already for every one of these reactions when you're doing malonic ester synthesis. And I'm asking you what two compounds are needed for the synthesis of the following. The first thing you can list out is diethylmalonate. So this should be automatically like one of my first answers for this synthesis. So I'm just going to use it, diethylmalonate, and something else. This is, I guess I kind of need to show you a reaction before I do this. Let's see. Yeah. So here's one that I had on my work on one of my worksheets. So I gave diethylmalonate and I made you react it with sodium ethoxide. An alkyl halide, H3O plus, and heat. So then my first step is again just deprotonating the alpha carbon, and there's only one alpha carbon here, so this one is deprotonated. Second step, I'm giving you an alkyl halide. So from here, it's just like a substitution reaction where I attack my electrophilic carbon and the leaving group leaves. So then write everything the same. And you have a total of 2 carbons that are being added to this. So a total of 1, 2. So that's what I should add here. 1, 2. That's something that's important too. For step number 3, there's kind of two things that you should know. So for H3O+, what that does is it turns all ester groups into carboxylic acid groups. So if I have 2 ester groups, all of them are going to turn into carboxylic acids. If I only have 1 ester group, that one turns into a carboxylic acid. And heat decarboxylates. So when you think about decarboxylation, something that I think about personally is CO2. So C double bond O. And that'll help you figure out like what you need to remove, because D means like taking off and carboxylate tells you what you're taking off. So then for number 3, the first thing I'm going to show is what the effects of H3O+, which again turns all your esters into carboxylic acid. So that's exactly what I'm doing here. Keep all your carbons. And so I'm just going to write under H3O+. The other one is heat. So heat, what it does is it decarboxylates. You have 2 carboxyl groups here. So notice how I have a carbon with 2 oxygens. Very similar to what you see right here, right? So then only one of my carboxyl groups is going to come off. Only one. So then I keep all my other carbons. So I'm going to highlight those. A total of 1, 2, 3, 4 carbons. So I'm just going to write 1, 2, 3, 4. 1, 2, 3, 4. Right. And that'll be my final answer. 1, 2, 3, 4. 1, 2, 3, 4. Yeah. So I got rid of pretty much CO2 and proton, which I don't even want to think about right now, but I'm just gonna write proton, like where that goes or whatever. But that's basically what you need for these reactions for the malonic ester synthesis. So then again, you have a malonate. I'm gonna ask you to like think of like, okay, first I deprotonate this right here, right? And then I need an alkyl halide. So that's the second compound that I need to see like what happens. And so what I want you to notice here is all of a sudden, like we only have 1 carboxyl group. Whereas in the beginning, when we look at this right here, I have 2 ester groups. So that's what the H3O+ did in malonic ester synthesis. We turned all of our ester groups into carboxylic acid. So we should have only have had a carboxylic acid, and that's what happened here. And one of them with the heat is decarboxylated, so it left. So then this right here should be my alpha carbon, which is this one right here, the one that was able to attack something. So then from my alpha carbon on, I have a total of 1, 2, 3 carbons. Those are 3 carbons that I added. So then what I'm going to do is I'm going to add an alkyl halide with only 3 carbons. 1, 2, 3. 1, 2, 3. And that will have been enough to synthesize enough to do my reaction of malonic ester synthesis, right? So then we do the same thing with this next one. Notice how I only have 1 carboxylic acid group. Again, H3O+ turns your malonate, so that's one of my starting materials over here. Always one of my starting materials. You turn your malonate into you're using H3O+ to turn the ester groups on malonic. Yeah, I'm just gonna say malonate. And after you turn both of them into your carboxylic acid groups, the heat decarboxylates only one. Okay, so then basically what I'm saying is you've already taken off something like this, and you only have the first step, right? Tells you to deprotonate, so that's what I'm having right here. I have a nucleophile. And now the second compound that I need is the electrophile, or the other things that are being added to my alpha carbon. For this one, did I mess up on this one? Yeah, I think I might have, I think I meant to do this. So instead of this, it's exactly the same thing. I'm just gonna add another carbon because this would make more sense. Okay, so now this one would have been my alpha carbon. This one is my alpha carbon, and I need to add on total of 6 carbons. 1, 2, 3, 4, 5, 6. So I'm just gonna attach those 6 carbons to a halide group. So anything bromine, it's a good leaving group. So that I added onto my malonate total of 6 carbons, and that gives me the thing that I was trying to synthesize for. It took me a long time to say, but yeah. See that one, a lot to process. So that I'm gonna skip from this one to the one that I was saying was similar. Acetoacidic synthesis. So acetoacidic synthesis, again, the only thing that's different between those two is the acetoacidic has a different starting material. So the starting material for acetoacidic is ethyl acetoacetate, which looks like this. See how it looks very similar, except for instead of 2 ester groups, I only have 1. And so some kind of reaction that I can use to do acetoacidic is exactly like the same one I did in the beginning. So first I deprotonate. Deprotonate your alpha carbon. So I deprotonated my most acidic carbon. And then second one, I can add an alkyl halide. So I'm just gonna add Br ethyl group. So my second reaction is to add, this is a substitution reaction. And I simply add 2 carbons to my alpha carbon. And then step number 3 can be H3O plus, which we know turns all esters into carboxylic acids. With heat. So heat, we know it decarboxylates. So carboxylate, I think of CO2. So I'm going to get rid of all of this molecule right here. And I'll be left off with a total of 1, 2, 3, 4, 5 carbons. So I'm just going to draw 1, 2, 3, 4, 5. There you go. And that should be my answer. So again, it's literally the same thing, just a different starting material. So then when I'm doing all of these, I should have the same starting material. So for this one, this will be my first reactant that I use. The second reactant, again, is going to be like an alkyl halide. So for this one, remember your alpha carbon. So locate your alpha carbon and see what's being added to it. So all of this left, right? And I'm supposed to be only left off with this part. I'm saying the right side left because that's when we did the H3O plus to make carboxylic acid, and then we use heat to decarboxylate. So all of that part is leaving, and I should only be left off with this part, right? So then all that I circled in the purple, so I think it's the cyclobutyl group, I need to add, and how I will add it is in the form of an alkyl halide. Just like that. Same thing with this one over here. Ethyl acetoacetate is your starting material. Again, all of this leaves, so we can forget about that. And all of this stays. I look at something on the molecule that I'm trying to synthesize that looks like what I circled in green. This looks exactly like what I circled in green. And so I look at my alpha carbon now. This is my alpha carbon. To this alpha carbon, I'm adding a total of 1, 2, 3 carbons. So that's exactly what I'm gonna do. I'm gonna add 3 carbons in the form of an alkyl halide. Same thing with this right one. Ethyl acetoacetate, because I'm doing acidic synthesis. We know that H3O plus and heat will decarboxylate all of this, so we don't even have to, we can forget about that. And I should have this group right here in the molecule I'm trying to synthesis. I locate that. I locate my alpha carbon, and I know that I'm adding all of this group over here. So I'm adding a total of 1, 2, 3 carbons. This is exactly what I'm going to do with an alkyl halide. There we go. Cool. For my aldols are still easier. I think the ones that I got confused with are the Claisen. The aldols, here's the trick to this one. So remember, looking back at your notes, you can use any ketone or aldehyde in order to form your beta hydroxycarbonyl, right? Any ketone or aldehyde. What I did was I cut this in half. So wherever my alkene was, I located my alpha carbon and I cut it on my alpha carbon. So basically what I did from there on was cut everything in half already, right? So I should have this on the left side and this on the right side, right? Just add an oxygen. Yeah. So then that means we're reacting two ketone groups in order to make this right here. You're gonna do that for every one of them. So locate my alpha carbon, cut it in half, giving you an aldehyde and another aldehyde, adding an oxygen, and those are the two reactants that you can use. So I'm just gonna add another hydrogen here just because it bothers me. Same thing on this one, alpha carbon, cut it in half. This is one of my ketone groups. And all of this will give me an aldehyde. And I attach an oxygen. Those are my two reactants. Again, you should be stopping this video just to make sure that you understand it and then look at your mechanisms and then try it on your own. But I think the most difficult part of all of this was to try to be fast in your exam because all of these take time. So then you should come up with tricks for yourself in order to save time and go through your exam quicker so that you can look back at it. So that's why I'm teaching you all of these. And they should all work. Find my alpha carbon, split it in half. I'm just gonna add my hydrogens just because it bothers me. And add an oxygen. Cool. For my Claisen. Okay. For my Claisen, let me see what I'm doing. Two molecules and ester react with each other to form a beta whatever, right? Okay, so then two molecules of an ester is what I need. And here's what I'm gonna do. I'm gonna do this one first right here. So again, look for your alpha carbon. This is my alpha carbon right here. And you can pretty much check it out. Here's a mistake that I would have made. I would have put, because it's the same pretty much. So you locate your alpha carbon and you can cut it in half, right? Here's the thing that's confusing though, is because you have a methyl group in there. So you're like, okay, what side does it go to, the left or the right side? Because I would totally go like, this right here would be one of my products. And this one right here would be one of my products. And that's like one of the ideas that I would have. Or the other thing that you can look at is, since I cut it in half, maybe the carbon methyl group on the alpha carbon is going to go on the left side. So then I would have, forgot this, ETO, boom, boom, double on, boom. OET, boom. Okay. Between these, because these I would totally get like confused. Your best answer choice is going to be the bottom one. We're doing Claisen, which requires two ester groups. And that's exactly what the bottom one is showing you. So you could totally write them both out in your exam, but just remember what an ester or what a Claisen reaction is. You're reacting two esters together. And so how I like justify this to myself is again one of my alpha carbons. So I just chose this one randomly as an alpha carbon. I had this one attack the only electrophile that there was, which is this right here. And it pops it open, right? So I should get something like this, and it's gonna look confusing. A little confusing right now. This, you have a negatively charged oxygen, you have OET, and you have this right here. So that's what you have. And then you remember that the ester group is a good leaving group. So then when you reform your carbonyl, this leaves, and you get this right here, ETO. Which is exactly like what I did here. So I used this to justify myself. So you should have two ester groups together, and just remember that one of your ester groups has a good leaving group, so one of them is going to leave. So locate your alpha carbon, and then you should have only a total of two ester groups. Okay. So then do the same thing over here. Locate my alpha carbon, which is right there. I should have two ester groups, so I'm just gonna say this left one has an ester group, so I can take all of these methyl groups with this one. So ETO, boom, boom, and alpha carbon that is tertiary, right? And so if I take all those methyl groups, that means that all of this is free to have an ethyl group on this side right here. So OET. So same thing over here. Look at my alpha carbon, which is right here. ET. I have no methyl group, so that makes it a little bit less confusing. But I take this carbon with me since I already have an ester group on this compound. And so I can add my ester to this right here. Oh, I forgot an oxygen. ETO, boom, boom, double. There you go. Now this last one on the left, I didn't start with this one because this one was a bit confusing to me, but this does apparently happen. So I said that two ester groups should be reacting with each other, but for this one we have an aldehyde and an ester. So I'm thinking this is like an exception because I did see this once and I was a bit confused by it, so I figured that I would include that here. Even though I doubt that they're gonna give you something like this, but I don't know. So I'm just gonna show this to you. I'm thinking this is an exception. So then I have my ester group right here, which we said we have an ester group, we can add anything to it. Oh, and that's what made it confusing. So this one's a bit like the one that we did up here. This is the alpha carbon that we would depronate right here. And so remember, you find your alpha carbon, you split it in half. Everything on this side stays the same. And everything on this side, you draw it out, and you add an oxygen. So this one was a little weird to me. I don't think you could find anything like this on your exam, but this is just something I just wanted to show you because when I saw it, I didn't understand it. But these are the main things that you should focus on. Okay, we have two more. Let's do this. Deichmann. Deichmann is intermolecular Claisen, so ester reacts with an ester. That means, again, if we look at this right here, it's intermolecular, so it's on one compound, and we need two esters. So that's what you need to keep in mind for this one. And you pretty much don't need a second compound to react this with. This is all going to be intermolecular. So then what I'm going to ask you to do is find the alpha carbon. Find my alpha carbon is right here. And I'm going to start the count from there. So that's what I'm going to do. 1, and I'm going to go all the way to my keto group. 5. 1, 2, 3, 4, 5. Okay, so then all I'm going to do is I'm going to write this out right here. So right here. And I start the count from this carbon right here, which is my alpha carbon. So 1, 2, 3, 4, 5. 2, 4, 5. On the 5th carbon, I have a carbonyl group. So I'm just going to write carbonyl group right here. And we know that Deichmann is 2 esters reacting with each other. So on this carbonyl, I'm just going to write another ester. Yeah. And that's like the trick for that one, right? So then we're going to do the same thing with the one on the right. Identify your alpha carbon, which is this one right here. I'm going to start my numbering from that. So 1, 2, 3, 4, 5, 6. Write this so I can have a starting point for myself. I'm going to start my count. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. On the 6th carbon, I have a carbonyl. Remember, Deichmann is 2 esters, so I'm just going to write an ester. And that'll be your intramolecular chalasin, otherwise known as Deichmann. And again, it's important for you to look at the mechanisms because that's going to help you big time. Like it's a whole aha moment when you see the mechanism and you look back at the tricks to do all of this. Last one, Michael. So for this one, you need a Michael acceptor, which is just the alpha beta unsaturated, right? Okay, let me see if I have my notes on this one. Let me make sure I'm good. For this one, I got confused on this one, but it's like easier once you figure out like how to orient everything. So I need an alpha beta unsaturated. Here are the 2 possible reactions that I would have done. This one looks very confusing, right? But I just used as many carbons as I could to confuse you. So this is an alpha beta unsaturated. My unsaturated I put right there, meaning that my other compound that I would react it with is like a ketone. So anything that can make what's it called? Carboxylate group. So ketone or an aldehyde, right? That's perfect right now. Another way that I would have done it, because there seems to be a lot of ways to do different things, but for this one, there actually isn't. The other way that I would have like mistakenly done it is like this, because this is still an alpha beta unsaturated compound, right? And I just add the rest of the carbons. It's a total of 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Okay, all my carbons are good. Okay, so then, oh my god, are all my carbons good? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 8, 9, 10, 11, 12. 8, 9, 10, 11, 12. Good. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12. Okay, never mind then. Looks like both of these would be like perfect reagents in order to make this Michael product. So then any way that you would have done it would have been good. So let me just check the other ones just to make sure that all these other ones are okay. So again, I just needed my alpha beta unsaturated and I needed something with an alpha hydrogen that I could deprotonate. And so from there on, I could like go do whatever I want, right? So for this one, I'm gonna cut it off here. I'm gonna let that one be my alpha hydrogen that I would deprotonate. And the other thing that I would do to make my Michael acceptor, which is just something that's alpha, beta, and saturated, is this right here. So then I count my carbons. I have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. So that should be good. Another way that you could have done it was like, oh, they would have been the same both ways. So yeah, we're good with this one too. Let's see if this next one is fine. It looks fine to me if you do it either way. So I'm gonna stop. I'm going to stop it right here where I have my available alpha hydrogen right here. Available alpha hydrogen. And I'm going to write everything else. And my alpha, beta, and saturated. I'm gonna count my carbons to make sure I'm okay. So I have a total of 4 right here. 5, 6, 7, 8, 9, 10, 11. 5, 6, 7, 8, 9, 10, 11. And we're good like that. And I'm pretty sure we're good to do it if we flipped it around. So like if we did this. Yeah, I believe this would be good too. And let me just make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 4, 5, 6, 11. Yeah, you should be good both ways. So any way that you decide to do it for this would be fine. Just make sure to identify your available alpha hydrogen to deprotonate and a Michael acceptor. And make sure that you don't drop any carbons, because that's the most important part about all of these basically, because it's easy to do it with all of these. Right on time. I believe we're done with all of the worksheet. So hopefully that helped you a little bit more with all of the named reactions. But I'm gonna make another worksheet, so part 2, to help you with everything else. This should be like the main thing. This was like the hardest part of my test, so I think this will really help for yours. I will see you guys in the next exam review.